To survive a complex environment, a system relies on adaptation, the ability of agents to independently respond to shifting, localized conditions on the ground. But an organization also requires coordination, the mandate that agents align their actions with one another to generate systemic synergy. These two imperatives pull in opposite directions. An agent cannot perfectly tailor their response to a localized anomaly while simultaneously mirroring the behavior of the wider group. Standard management theory often treats this friction as a cultural deficit, prescribing better leadership or more open communication as the cure. This friction represents a strict mathematical optimization problem. When the fragile equilibrium between these two competing forces breaks down, the entire organizational structure becomes mathematically and fundamentally unstable. To solve this imbalance, we look at the role of the principal. This is the central intelligence, or headquarters, of the organization, which possesses valuable global data. The principal's task is to design a public signal, a method of broadcasting specific information to uninformed local agents to guide their individual actions. This introduces the economic framework of Bayesian persuasion. Within this model, the principal controls exactly what information is acquired and disclosed, structuring the data to optimize the agent's equilibrium state. Economist Wataru Tamura recently formalized how to solve this. By mapping organizational incentives onto mathematical network topologies, a principal can calculate the exact threshold of what data must be shared and what must be withheld. Tamura's 2025 paper reveals that in complex networks, providing maximum transparency frequently destroys organizational alignment. Optimal systemic performance sometimes requires the principal to enforce minimum transparency. We can map this dynamic by establishing a baseline environment. At the center is a single principal, surrounded by n disconnected agents. Each agent faces a unique environmental challenge, defined as their local state, xi. Based on that state, the agent executes an ultimate decision, or output vector, defined as their action, AI. If coordination were not a factor, an agent's optimal action would perfectly match their local state to maximize their individual adaptation. Now we introduce the critical organizational constraint, beta. This variable represents the importance of coordination relative to adaptation. A high beta acts as a heavy penalty, mathematically punishing agents if their actions deviate from the network, forcing alignment. Conversely, a low beta loosens the penalty. This allows agents to prioritize their local states over group cohesion. Beta serves as the organization's genetic code, dictating whether the system operates through fragmented agility or rigid uniformity. In practice, coordination occurs across specific relationships and network paths rather than uniformly across a firm. We map ideal coordination connections, links that benefit the organization as a whole, as the synergy graph. Overlaid on this is the incentive graph, representing actual, privately motivated coordination connections naturally forming between individual agents. Discrepancies emerge where agents have a strong private incentive to coordinate with a peer, even though the broader organization gains no benefit from that connection. Laplacian matrices are used to measure the physical tension and structural limits created by these differing graphs. When private incentives mismatch organizational design, agents' natural behaviors misalign with the principal's goals. If the principal shares all local data, agents utilize it to follow private paths, pulling the network out of ideal alignment. To prevent this, the principal must use strategic information withholding to deliberately weaken the pole of the incentive graph. In situations where private incentives and organizational synergy diverge, unrestricted transparency facilitates systemic dysfunction. If full transparency destroys alignment, what information can the principal safely share? Tamura's research establishes that regardless of the network structure or the weight of beta, the optimal signal must always inform agents of the average state of the environment. Sharing the average state establishes a universal focal point. It satisfies the agent's private incentives to align with one another without injecting the variance that leads to local chaos. If the principal withheld this average state, agents would try to guess the baseline using their flawed local data, causing compounding estimation errors and massive coordination losses. The average state serves as the universal anchor of organizational performance, fulfilling the need for coordination while preserving the capacity for localized execution. Since the average state is a constant in the signal, the principal must calculate exactly how many localized data statistics to disclose alongside it. The dimension of the optimal signal, the number of local truths revealed, is determined by a metric called the algebraic connectivity of the incentive graph. As coordination needs increase, the principal reduces disclosed local statistics. The curve flatlines at minimum transparency, disclosing only the average state and withholding local data. Network topology determines this slope. Dense networks sustain a gradual release, while sparse networks drop to minimum transparency much faster. The mathematical structure of the network itself dictates the exact point where transparency shifts from an organizational asset to a systemic liability. Effective organizational design relies on calculating the specific mathematical tension across the incentive graph. A leader's most powerful tool is carefully engineered information scarcity. By anchoring the entire system with the average state and deliberately pruning local noise, a principal orchestrates alignment. Systemic alignment is the product of mastering this calculus of transparency.